Okay, we start with the question of what should be the period of the simple harmonic motion you get if you displace this from equilibrium. Now, I don't have a good place to put it. The equilibrium position is not real close to this. I need to have it out further. But you get the idea. Everybody's seen this. It'll oscillate, then it'll come back. Okay? To measure well, we can measure the torque on this thing to an extent. By pulling it back, and actually it'll demonstrate better if I do it over here. Okay. Now if I pull it back here, we see this rubber band, which is currently more or less circular, stretches out. And if we stretch it out to the point where the rubber band is about, half a centimeter wide, well, if we could get this thing back to equilibrium, we could estimate the displacement, the angular displacement from equilibrium. Then I can take this, and we're not going to demonstrate that because I don't want to carry the balance over here, but I got two weights, one with a hook on it, on a pan balance. I've got them equal weights on both sides. I pull up on this thing, and
Maybe stopwatches.
well, we could use them. Thank you, Tom.
There are two that I suspect are workable.
Appreciate it. So on the hook weight, we just pull this thing up till it's about the same width. Of course, we have a smaller hook till it's about that wide. And we see that then we have to add 10 grams to this side to get them back into equilibrium. So we figured that this thing was exerting about a 10-gram force, but not a 10-gram force. That corresponds to about a 10,000 dyne force, okay? Or about a tenth of a newton. Okay, now we see that the actual equilibrium position of this thing is over this way a little bit. And we judged that we were at about 7/10 of a radian from equilibrium when we did that. So we want to estimate what should be the angular frequency or the period of oscillation of this thing. It's oscillating right now. I'm getting about 1,001, 1,002, 1,005, 1,006, 1,007, 8. About 8 seconds for half a cycle, about 16 seconds for a cycle. Now we want to relate that to the quantities we use in simple harmonic motion. So I ask, what should be the angular frequency of this thing? The angular frequency of the motion of this circular model, and so forth. Well, it's a little more complicated, a little less familiar with a rotating beam, so we go back to the pendulum, okay, and the premise of simple harmonic motion. So for linear simple harmonic motion as opposed to angular, we reconstruct the derivation, which we've done at least half a dozen times, and which you are going to have to be able to do for the final. Okay? Basic premise for simple harmonic motion is the net force is negative kx, where x is your position with respect to equilibrium. That's a linear restoring force. Now that means that ma is negative kx. Now what are you going to do with that? How can you rewrite this? Because you have an a and an x. Is a related to x in any way? Well, a is v prime. Well, now you got v prime and x. How's v prime related to x? Well, another derivative of, well, a second derivative of x is your v. And those are just your basic definitions of velocity and acceleration. And You're pretty familiar with that. Had a little trouble dragging it out of people last time. And it should be right there, okay? Should be something that you don't just recognize when you see it, you got to be able to pull it out when you need it, okay? So anyhow, you get the equation x double prime equals negative k over mx. Now, you haven't had a differential equation. Of course, it's a very simple premise that you can use to solve an equation like this. You assume x is equal to e to the lambda t, or the e to the rt, usually differential equations. You make that assumption, and you see what r should be. In this case, r is going to be negative k over m times I. What's I?
Last time gradient squared. Addition of all those.
That's capital I.
Oh.
We're talking about numbers. What's the number I?
Oh, it's a number. Square root of negative 1.
Good, good. Not everybody knew that last time. Okay. So I'm glad to see that we have an answer to that one. Okay. Okay, so the solution's got to be a cosine function or sine function or e to the it type function. Like, what's the second derivative of e to the it? Well, what's the first derivative?
Just e to the x.
Well, the derivative of e to the x is e to the x. Well, x didn't have any number in front of it. What do you do? What's the derivative of e to the 2x?
2 e to the 2x.
Okay, so why couldn't you tell me what the derivative of e to the it was?
I squared e to the it.
That'd be the second
The
derivative.
second.
First derivative would be e to the it. I think you were answering my original question. You wouldn't have squared it unless you had a darn good reason. Okay, so you got e to the it type function. Well, I squared e to the it is, well, what's I squared?
Negative 1.
Yeah, so it's negative e to the it, right? So you see, if you took a second derivative of e to the it, you would have a negative of e to the it, right? So if x was e to the it, x double prime would be negative e to the it. Okay? So there's one function, okay? One function that has a second derivative. It's a multiple of itself. Well, let me just push you a little further, because you're doing pretty well with this. Okay? What would you have to take a derivative of to get negative k over m times x? What multiple of the it would you have to use? Like you're going to use a chain rule. How are you going to get a square root of k over m from two applications? Yeah, for doing two derivatives, so it's a chain rule. Well, if you had e to the 2t, no i's, just e to the 2t, what would your second derivative be? 4e to the 2t. Okay, so that's what I knew you were going to say. Okay. If you want to get 3e to the t, or 3e to the whatever t, what's the whatever?
Must be 3.
Well, if you do derivative of 3e to the 3t, you're going to get 9e to the second derivative. You're going to get 9e to the 3t, right? What would you have to take the derivative of to get 3 times your function?
1 to the 3t.
No, because second derivative of 1e to the 3t is 9e to the 3t. So what do you have to have in front of t to get 3 times what you started with? Sorry?
1/3.
No, you get 1/9. Now how did you get e to the 4t?
How did I get e to the 4t?
Sorry? It did the derivative of e to the 2t, and you got second derivative of e to the 2t, and maybe not saying my derivatives right. Second derivative of e to the 2t is e to the 4t, right?
Yeah.
Well, if you wanted to get e to the 3t, or 3 e to whatever t from two derivatives, what would you have to have? I heard square root. That's what I was listening for, so I'm sorry. Need to put my hearing aid in. Can't hear what you're saying.
3.
Sorry? E to the what?
E to the, I don't know, square root of 3t.
Yeah.
Doesn't sound right.
Yeah. Yeah. That's what I thought you were saying. You're saying it kind of low because you're thinking through it.
Yeah.
But I could tell you were thinking right, okay? So it'd have to be e to the square root of 3t if it was going to satisfy this with a negative 3 in front of it, right? Or with a 3 in front of it. And if you want a negative 3 in front of it, you do e to the I times square root of 3t. Okay? Now, how would you get a negative k over m?
E to the k over m.
E to the what?
E to the k over m.
Well, if you did two derivatives of e to the k over m, what would you get?
K over m squared. K
Yeah.
squared over m
Yeah, but
squared.
you don't have k over m squared. You just got a k over m, right? So what do you have to do?
You'd need the square root of those.
Again,
You would need the square root of those.
square root of,
Twice, I suppose.
square root of what?
K over m.
Yeah. So if you take two derivatives of e to the square root of k over m, you get square root of k over m times e to the square root of k over m, right? Well, k over mt, okay? Okay? So, if you had an I in there, e to the I square root of k over mt, then you get an I squared times k over m, right? So e to the I square root of k over mt would have a derivative that's equal to negative k over m times itself. Okay?
Yeah.
Now you don't necessarily have to see that in terms of e to the it. You can see it easily in terms of a cosine. What cosine function would have a second derivative equal to negative k over m times itself? Well, let me just please. Okay.
Second derivative of it. Second derivative.
Well, what's the second derivative of cosine of 2t?
2 squared negative.
Yeah, negative 2 squared times the cosine of 2t. First derivative is negative sine with a 2 in front of it. Second derivative will be negative cosine with another 2 in front of it, making 4, right? So how would you get a negative k over m?
Second derivative of cosine of k over m.
Well, second derivative of cosine of k over m would be k squared over m squared times the cosine of k over m. Negative k squared over m squared times the cosine, right? So you're going to have to do that square root of k over m again. Cosine of square root of k over mt. For each derivative, you're going to get a square root of k over m. Do it twice, you're getting the k over m. Okay? So, make sense? You really got to understand that.
Sure.
Okay? So cosine of what double prime is negative square root of negative k over m times the cosine of the same thing? Well, I asked, what's the cosine of what is equal to negative 4 times the cosine of what? Well, that would be 2t, right? If the what is, the question mark is 2t, then you're going to get a negative 4 cosine of 2t when you take the second derivative. Okay? Now, if you want this, well, there it is. Okay? Easier to see if you're not trying to do it in your head. Okay? But that should make perfect sense to you now since you pretty much got it. Well, you got to know that. You got to be able to answer that question. Okay? Yeah, it's been a few years since you had your calculus course. Of course you got it. You got to think these things through as they occur. Okay? And since this occurred in the first week, it's maybe time you did that since the finals next week. Okay? And you got the bits and pieces of it. You just got to get it to where it's really, really clear. Okay. So, and it doesn't hurt if you add a phi in here because the phi is constant and it's immune to derivatives. It just goes away when you take the derivatives. It's constant. Okay? So derivative of cosine squared of k over mt plus phi is still square root of k over m, negative square root of k over m times the sine. It's the same thing. Okay? So we have this, and we have this as a possible solution. Because if the second derivative of this equals this, well, a is just a constant. So I just multiplied both sides here by the same constant. So this is my general solution. It's got two arbitrary constants. Got the arbitrary constant a, got the arbitrary constant phi. Because we've essentially done two integrations, although we haven't really done integrations. But this is the same as every time you do an integration, you get an integration constant. Okay? I could go deeper into that idea, but that's enough right now. Because again, we're not basing much of the first semester on integration. Well, now you can see that if t, well, how much does t have to change? First place, the argument of the cosine, whatever's inside of here, to go through a complete cycle of the cosine function, and think about going once around the unit circle, whatever's inside of here is your angular position on the unit circle. It has to change by 2 pi. From wherever it is, it has to change by 2 pi in order to get a complete cycle of the cosine. In a complete cycle of the cosine, if you look at the circular model, okay, and the x-coordinate is, we go around the circular model, the x-coordinate goes through a complete cycle, okay? So if t changes, well, what does t have to change in order to make this change by 2 pi? Well, the only thing that's going to change here is the square root of k over m times t, right? Phi is just going to be wherever it is. This is what's going to change. So now you said something. I'm sorry.
I was saying 1 second, but frequency, basically, angular frequency? Or
Yeah, that would be the angular frequency.
Period.
But t has to change by enough to make square root of k over mt change by 2 pi. Okay? Well, to answer that, if you think about it, I'm going to give it another shot. Well, let's do it with easy numbers.
It needs to change by 2 pi.
Well, how much does t have to change if 2t is going to change by 2 pi? Well, how much does 2t change if t changes by 3?
Two t changing.
Sorry? So, I'm sorry, John.
I don't know.
We got 2t. t changes by 3.
Yeah.
So how much does 2t change?
3. The whole thing changes by.
No, if t changes by 3, t changes by 3, but 2t doesn't change by 3.
3t times 2.
You're getting there. Changes by 6. If t changes from 5 to 8, okay, then 2t changes from 10 to 16, right? Okay, 2t changes from 10 to 16. How much changes that? Sorry?
6.
Yeah. Now, if t changes from 17,593 to 17,596, by how much does 2t change?
3.
Yeah. 2t is going to change by twice as much as t changes by, right? Okay?
Yeah.
Well, then, if t changes by 2, how much does square root of k over mt change by?
By 2 times the square root of k over.
Yeah, by 2 times the square root of k over m. Okay? Now, if you want square root of k over mt to change by 2 pi, how much does t have to change by?
2 pi times. What is it? 2 pi times the square root of k over mt
Well,
is.
t's not going to be part of what t changes by, but you can think it. And I'm not going to make you suffer anymore. I'll save that for another question. Okay? But you get the idea. Well, if k over mt changes by 2 pi, then t has to change by 2 pi over the square root of k over m. Okay? Like if I want 2t to change by 12, how much does t have to change by?
6.
Yeah. You're going to divide whatever change you want by that 2, right? By this coefficient. So for this, by the same reasoning, you're going to do this. Okay? And 2 pi divided by the square root of k over m, that's like 2 pi radians divided by the square root of k over m radians per second, giving you this many seconds. Okay? That'll be the period. So the square root of k over m is what you call the angular frequency, which is the same as the angular velocity of that point moving around the reference circle. If you're moving around the reference circle at pi radians per second, then in 1 second you're over here at pi, in another second you're back at 2 pi. Your period is 2 seconds. Okay? And you want to think that through. You want to really understand that. Now, one thing that I noticed, and I'm not sure why, but nobody comes out of second semester pre-calculus with any concept of how to graph a function like this. Okay? You're told a few rules to memorize. You use them long enough to pass the test. You never had a concept, so it doesn't persist. Okay? You want these concepts, you want to think in terms of concepts and not formulas, as I keep preaching. Okay?
Yeah.
So, still trying to wean you from that. You're doing a pretty good job of it. Okay? Let's hope it. By the end of next week, you're totally fluent with it. It's a little much to hope for, but you're capable of it.
Oh,
Especially if you kill a couple of deer and get some meat in the table, it'll nourish you. Okay.
I wish I could focus better on it. Yep.
Yeah. Well, you're out there waiting for a deer to show up, thinking stuff through. Yeah, you don't want to do that. Hard to separate. You don't really want to be thinking about this when you're out in
It's
the
a good
woods.
way to pass time.
You get yourself hurt, shoot somebody. Besides, you're out there to clear your mind, okay? Among other things. So anyhow, Okay, so you know this, and omega, doggone it, is the square root of k over m. Okay, using now omega, and that's where omega comes from. And one of the first things I told you is there are two things you need to know about simple harmonic motion. There's your premise. Net force is negative kx. Omega is the square root of k over m, and that gives you your circular model. And then all the details in between. Okay? Understand it as deeply as you can. Because we were unable to address this problem of the beam in our last class. Okay? We were just unable to get the pieces together. We knew bits and pieces of it, but we couldn't put them together. And if you understand these principles and where everything comes from, something as essential as omega equals square root of k over m is not just a formula. It has meaning. Okay? So that we can translate this to the angular simple harmonic motion, then apply it here. And I got something ridiculous for the answer, so I want to look at it again. I'm pretty sure I've got too many zeros in this, but every time I look at it, I still get that extra zero. Okay? I could go to a calculator, but who believes that? Okay? I never believe a calculator. I'll work it out, then I'll punch it into a calculator if I really have to build something with it. Okay? Otherwise, leave it to the engineers to get it right. Okay. So an angular simple harmonic motion, you have exactly the same form you have here, except it's a net torque, and we've got to do this in terms of net torque because it's torque that provides the angular acceleration of a rotating object. Okay? Whereas this is something moving along a straight line, the other is something that's rotating. So we started out by getting the torque. Okay? We figured we were applying a force of a force equivalent to the weight of a 10-gram object by what we did on the balance, and that force is mass times acceleration. 10 grams times 980 centimeters per second squared, roughly 1,000 centimeters per second squared. Multiply that out, we get about 10,000 dynes. Okay? So, you know, we're applying this. There's your net torque. And it is a net torque, so I can put a net on that. You can't read it, but you know it must mean net. Okay? So there's our net torque. Now the other thing we know, instead of mass times acceleration, we have moment of inertia times angular acceleration. And instead of x, of course, we've got theta. Theta is our measure of position. Okay? And this is theta measured with respect to the equilibrium position. Okay? So I should say
The origin or something.
x is, well, you can put the equilibrium position anywhere you want. But if you're on an x-axis and want to use x as your position, then you better have your equilibrium at the origin. If your equilibrium is at 10 centimeters, then F net would be negative k times x minus 10 centimeters. Okay? Wherever the equilibrium position is, remember, you have flexibility in how you position the x-axis, and sometimes you don't want it at the origin, and you got to then do the translation. Okay, in any case, x with respect to equilibrium, or theta with respect to equilibrium. Okay? Okay, anyhow, we have this. Because net torque is product of moment inertia and angular acceleration, totally analogous to net force is mass times acceleration. Okay? And the mathematical aspect of this is exactly the same as it is here. It's just that you use different symbols for some of the quantities, and they have different meanings. But the mathematics comes right out. Theta double prime is your angular acceleration. It has to equal negative k over I times your theta. Okay? Now, we got some notational problems. This K looks a lot like this K, but this K is in units of torque per unit of angle, like dynes per radian or meter newtons per radian. And it's not dynes, it's dyne centimeters per radian. And you know, when I wrote this down, this, I've got dynes here, it's dyne. I'm just trying to figure out where to put it. It's 9 centimeters. Okay. No, never mind. That's torque. Forget it. No. Okay. It's 10,000 dynes times 10 centimeters. And there's my extra zero. That was just ignorant, but you're used to that, okay?
Yep.
And then I've got the right units, dyne centimeters per radian, okay? I need another zero here. I'll just slop it in by changing that 1 to 0, okay? Okay, so I screwed up. I figured out where I screwed up. I knew I was off by a factor of 10 because I got something like 50 seconds here. And that thing takes about 16, so I knew I was off by a factor of 3, and 3 is close to the square root of 10. So, having written this down ignorantly, you know, dynes is not even the unit of torque. Dyne's a unit of force, right? I did this. I missed a 0. And now it's going to be about right. Okay, well, we'll fix that in a minute. Okay? Back to here. It's your angular acceleration in terms of theta. Angular acceleration is the derivative of the angular velocity, which is the derivative of your position, angular position theta. So alpha is theta double prime. It's the same equation we have here, except we have thetas instead of x's. And now it gets a little confusing notationally, because we have a couple of omegas involved here. We've got the omega, that's your angular frequency. We also use omega for angular dang velocity. And I wanted to use a different symbol. I usually do. So I looked at your book, which I seldom do, but I looked at your book. They use omega ambiguously. I looked on the internet. I went to Wikipedia. They do it too. Well, if it's good enough for them, they know more than I do.